hopefully you'll find this talk useful for you. And like I said, this is an introduction, so hopefully you can follow up deeper into these topics. So let me start by sharing my screen. All right, move some things around here. All right, can you see my slide? All right. So introduction to flow assurance and multiphase flow conditioning. So yeah, thanks for the introduction again. This is an outline of my presentation. I will, mainly two parts, which is the flow assurance section of the presentation, then a multiphase flow conditioning section, and then I will close with some conclusions and closures how these two interrelate. So the first part, flow assurance. So flow assurance is the combined analysis of multiple areas of expertise that ensure the successful and profitable flow of hydrocarbon streams from the reservoir to the point of sale. So you can see on the right here, one example of one of the flow assurance expertise, which is slug flow. This is in a vertical riser, and you can see the transient nature of that flow. So each of these areas of flow assurance by themselves can be very specialized. So each area can be worth multiple PhDs and developments. And so it goes very deep in the technical aspects of each of the areas that involved. So why we want to work on flow assurance? Well, there are multiple challenges there as the oil industry produces into deeper and deeper waters with cold temperatures, challenging fluids that have challenging fluid properties. All these developments create a very difficult task to ensure the fluids are properly flowing from the reservoir to the separations or topsides or separation facilities. There are complex risks, and it's not limited only to offshore developments. Onshore and Arctic fields also can have some flow assurance issues due to low temperatures or other challenges with the fluids. So here's a typical production system. So you have from left to right, the natural flow will start from the reservoir and the wells, and then it will go into a typical subsea flow line and a riser. And then these fluids will be handled either offshore in a topside processing platform or in a processing facility. So maybe this is an onshore facility in a gathering system or an onshore terminal. But anyway, the transport of these fluids from the reservoir all the way to the processing facilities has many challenges along the way. As the fluids flow, you can imagine out of the reservoir at high pressure and higher temperatures, they have to overcome all these pressure drops through the flow line as the pressure changes along the flow line, changes in geometry and changes in inclination angle, steep risers. And also, don't forget that this flow line is on the seafloor, and there's a significant colder temperature in the seawater at the bottom of the ocean. So there's a temperature gradient between the fluids being transported and the wall of the flow line, and all this changing occurring in a complex fluid such as a crude oil may generate a chain of issues that you have to be aware of. So these are the most common, famous, worst issues that you have to deal with when you're dealing with the multiple studies that involve flow assurance. Unfortunately, due to the lack of time today, I'm not gonna go through every single one of them, but I'm gonna highlight some of them so you guys get a very good idea of the nature of the challenges with some of these areas of expertise. So we have hydraulics, multiphase flow, wax, hydrates, asphaltenes, scale, naphthanates, emulsions, foam, solids transport, erosion, fatigue, and corrosion. And they can be classified in different areas. Some of them are operational by nature. Some of them can be classified as the ones that create blockages or increase frictional losses. Some of them are a threat to the integrity of your facilities. And well, some of them are a combination of all of these three issues that I just mentioned. So, And one last, it's not an issue, but it's something that is very important, is to do a proper fluid property characterization, because that is going to affect all of these flow assurance studies will be affected if you don't do a good job in your fluid properties characterization, all your predictions, all your models, for all these issues will be wrong. So you have to start well with a good foundation with a proper fluid characterization on the fluid properties. So let's start with multiphase flow. So I'm showing here an example of a horizontal flow pattern map as an example of one of the cases that you could see in multiphase flow. Multiphase flow and flow patterns is basically the configuration that two or more phases have inside a pipe as they rearrange themselves as a consequence of the velocities, but also for a particular pipe diameter, inclination angle, and fluid properties. So for that, some of the studies in multiphase flow simplify this problem, the complex problem subdividing it into smaller pieces, which are different flow patterns, which have different submodels for each region. So for that, they have created this fictitious variable called the superficial velocity, which is a velocity assuming that the other phases are not present in the pipe. So you just calculate it's a flow rate divided by the area of the pipe. And in this case, we're showing a superficial velocity for liquid and a superficial velocity for gas. And with that, based on experimental data and different models have been developed to classify each of the different regions. So we have stratified smooth region where you have gas on the top and liquid at the bottom. But if you increase the gas velocity, you can have stratified wavy, where you start to generate ripples, waves at the interface between the gas and the liquid. If you further increase the gas velocity, then this liquid at the bottom starts to creep up the walls and coat the whole perimeter of the pipe. And the waves at the interface of the gas liquid and from the interface, they start to rip off droplets and generate droplets and train into the gas core. Similarly, at other velocities, you have other flow patterns, such as at higher liquid velocities, you have slug flow, which is in this case, we call it slug, but it's actually a hydrodynamic type of slug, which are relatively short slugs, but it's an intermittent flow of gas and liquid, which in some cases can be problematic. There are other transitions between slug and annular flow where you can start to see characteristics of both flow patterns. And finally, at higher liquid velocities and relatively low gas velocity, you have dispersed bubble flow, which is basically bubbles dispersed in liquid, kind of like a fish tank, right? When you have bubbles dispersed in the liquid. So that helps to visualize it. So as I mentioned, this is dependent on pipe diameter, inclination angle, and fluid properties. The moment you change one of these, you have to generate a whole new different map. If you change the pipe diameter, you cannot use the same map. You have to generate it again using the corresponding models. If you change the fluid properties, you have to adjust the curves for those fluid properties and so on. So I'm showing only the horizontal flow pattern map, but you can imagine that there are maps from horizontal all the way to vertical and everything in between, right? To characterize the flow at different velocities. So the hydrodynamic slugs are formed due to the instability of the waves at certain flow rates. This, as I mentioned, I'm gonna call it here as the label of operational to remind you of that previous slide where I showed with all the other issues. But there are not only hydrodynamic slugs, there are other types of slugs. There's the terrain-induced slugs, which are caused by flow lines. As you remember the picture where I showed the flow line with the different elevation profile, and there are flow lines with different geometries, and all these geometries, especially the low spots in these geometries, can become points where you can generate long liquid slugs. And these liquid slugs can become, problematic if they build up multiple pipe diameters in length, and they eventually get produced and they can overwhelm a separator. There are operationally induced surges that occur when there are transitions between your normal operation in the field, and then you switch to either you're adding more wells or you doing some other operation, like a pigging operation, then you create a new slug in the system that was not, out of the norm. So, what all of these have in common is that your facilities, namely the separators on the top sides, can become overwhelmed if these large slugs flood the separator, and basically they start carrying over liquid to other subsequent processing facilities that are meant to handle gas, or mainly gas. So you can see that there are problems from facilities, from vibrations, from the energy of the slugs. The slugs have a high momentum because of the slug is basically a plug of liquid with high velocity. So that can produce damages in your facilities, produce problems with separation. But anyway, they can be problematic if not addressed properly. One of the other issues that I want to touch today is wax or paraffin deposition. So wax, it's a high molecular weight component in the oil that precipitates as the temperatures drop. So remember I mentioned that these flow lines are, we have subsea flow lines that are exposed to low temperature and close to the sea floor, where the seawater can be around 4 centigrade degrees, and creating a temperature gradient between the warm oils and the cold pipe wall that you have. And that temperature gradient can drive the formation of paraffins, first suspended in the oil, and then later on deposited in the wall against the pipe. You can see here a picture of what they might look in the lab, and this is a nasty picture of a wax with not only wax, but also chunks of probably some solids that were flowing along in the pipe. And they can be, they literally, going back to this plot, they can build up and continue to build up on top of another layer, reducing the area available to flow, increasing the pressure drop to the point that you really need to clean that wax if you want to continue producing. So again, this is a reminder, this is in the blockage region of the issues in flow assurance. So there are different shapes in what that deposit may have a different profile depending on different combination of velocities and fluids and flow patterns, but they may produce different profiles and different deposits of different softness, if you will. So to manage this, they do flow line pigging, which if you're not familiar with a pig, is basically a device that you insert at one end of the flow line and push it along the flow line to scrape the walls and literally just clean like a plumber, push all that wax all along the flow line and get the wax out on the other end where you can, properly handle it later on and reestablish the diameter available for the fluids to flow in the pipe. You can handle it also from the thermal point of view with insulation or pipeline heating. There are some technologies to have long flow lines where wax will be an issue that you can do electrical heating for several miles long. There are some inhibitors that we have to find out if they actually work or not, but some vendors claim they do. And there's called cubing technology, so different approaches to mitigate this issue. All right, hydrates. So hydrates is a combination of water and other small molecules that produce an ice-like cage structure that basically traps gas and water and produces a blockage of a solid very similar to ice. And these blocks are nasty. I mean, they can create disruption in flow lines that last hours, days, or weeks. So it's very important to understand them and address them and avoid them, right? Avoid them in the first place. So many of the things that they do, like I'm showing here in the lab and from these Sure Flow Solutions pictures that they share with me, they have different tests where They do one with a rocking cell where they have samples and they do tests at pressure and temperature. They rock the cell, they rock sideways, or they have one that is like this static mixer also at pressure and temperature where they can test the hydrates formation. Of course, there are other places like Tulsa where they have flow loops where you can test hydrates. So hydrates occur at a right combination of temperature and pressure. And I say right, quote unquote, because you don't want that combination. But unfortunately, that combination is high pressure and low temperature. You may have, let me show you here. You may have a temperature profile from your wellhead to your riser under normal conditions. Let's assume that this is your temperature and pressure profile. And you're outside of the hydrate risk region. You don't want to be here. But let's suppose that something went wrong topsides and they have to shut down the operation for a few hours and your fluids start to cool down. And your temperature, suddenly your pressure, the temperature profiles start to drop and you start to go inside these hydrate regions. So that's when you need to know, do all your studies and thermal analysis and transient thermal analysis to find out how many hours of understand your fluid, so to understand how many hours you have until you need to take an action and take other measures. So here's a video of that experiment with the static mixer characterizing hydrates. Anyway, asphaltenes. So asphaltenes, it's a high molecular weight compound. It's a mixture of carbon, hydrogen, oxygen, nitrogen, and sulfur. And they create, as opposed to wax, that wax is a soft deposit, asphaltenes are a hard deposit, and they're not going to melt. So they're difficult to deal with. You cannot melt them, the hot oil wouldn't work. So in order to deal with them, what you end up using is solvents such as xylene or toluene to remove the blockage. But you can see from this picture, you get an idea that it's almost like you're building up rocks or asphalt in your wells. So the way they occur is that initially the asphaltenes are suspended in the oil. So the oil are these black linear structures that represent alkanes. And the asphaltenes are these structures that are high molecular weight. They're around 500 to 1500 molecular weight. And they're surrounded by these red resins that act like surfactants. And by surfactants, I mean that they have a head, which they have similar properties to the asphaltene on the head side. On the tail, they have similar properties to the alkane chains. So they keep suspended the asphaltenes in the oil like a micelle, similar to a stable emulsion that you have, like emulsions, similar to mayonnaise or other emulsion. In this case, it's a nasty emulsion that has asphaltenes in the middle. When pressure and temperature change, either from pressure drops, there's some intermediate pressure at which these structures are no longer stable, and then they basically, the stable micelle breaks, and then the asphaltene chunks start to precipitate, and they can start to flocculate with each other and then create this. You can imagine these are like nasty molecules, like cockroaches, if you will. So they're giant molecules, and then they will start to flocculate and precipitate and create this deposit, of asphaltene deposit. So they can occur under, again, the right combination of pressure and temperature, but also they happen in when you mix different crude oils of different formations, depending on the chemistry of the different oils. You should check for the potential of asphaltenes formation when you do that. So I guess the only advice I can give you is if you're dealing with this, you need to find yourself an asphaltene expert to help you address this. Corrosion. So corrosion, I'm not gonna talk about this as a corrosion area point of view as a corrosion expert, but more from the flow assurance, what a flow assurance engineer can do to help a corrosion engineer do their job. So from corrosion point of view, the flow assurance engineer can help the corrosion engineers understand how the phases are flowing inside the pipe. So I'm showing here this figure where we're showing, suppose in a horizontal well, you have gas or a horizontal flow line. You have gas, oil, water, and solids at the bottom. At low, let's suppose gas velocities and low liquid velocities, you have solids settling at the bottom of the pipe and water and oil and gas stratified. So if you have a presence of corrosive components in your mixture, like H2S or CO2, this water is very corrosive, and you're gonna have a mixture of corrosive water touching the bottom of the pipe and the perimeter of the pipe, and these solids, it's a bad combination for a corrosion to start occurring at the bottom of the pipe. So that's one problem. Additionally, you have gas on the top, and there's no liquid protecting the wall on the top of the pipe. And again, if you have H2S at high pressure, it's a highly corrosive environment, you want the liquid to touch the top of the wall to help you protect that pipe. And in many cases, my understanding that most of the corrosion inhibitors are soluble in the oil phase, but not necessarily they are good inhibitors that are soluble in the water phase. So you want to try to have a combination of avoiding the water touching the wall of the pipe, but also have a corrosion inhibitor program. So anyway, if you increase the velocities, you can see that maybe you have velocity sufficient to have the solids to move, but still not enough for the oil and water to mix. If you keep increasing the velocity, then you may be able to have sufficient velocity for the liquid phases to mix. And then you can have either the water dispersing the oil, which would help you to have, then you're isolating the water as droplets, and then the oil will be touching the pipe instead of the water. That's directionally correct. You want to do that. But depending on the water cut, that may not happen. If you have high water cut, then what you're going to get is the oil dispersing the water. So anyway, I'm not gonna go through all the words in this slide, but I just wanted to get you the message of the combination of what happened to the phases, and from the multiphase flow point of view, point of view, so you can understand how important it is to know where the phases are as they carry some of the chemicals that are going to help you to mitigate this issue. Ideally, if you kept increasing the gas velocity, you could have an annular flow, and the liquid will creep up and cover all the perimeter of the pipe and protect the whole pipe. So in some cases that's possible. You want to design for it. You want to design the pipe diameter based on that, or you want to modify your operational guidelines to find the flow pattern, the configuration that works best for your field. Anyway, this slide is a summary from some study that was done in 2004, and it's summarizing some of the the shutdowns that happened due to different flow assurance issues. And I mean, this is relatively has a few years ago, but still you can see that at least for this case, there was a lot of a chunk of shutdowns due to corrosion issues, sand, scale, and on other issues. So as you can see, there are multiple reasons that the point is that they're all problematic and create disruption of flow. And when there is disruption of flow, there's revenue that is being delayed, and then someone is not going to be happy if your $1 billion field is not producing for a few days. So anyway. All right, this brings me to my second part of the presentation. That's the laser pointer. So multiphase flow conditioning. Multiphase flow conditioning is an area relatively newer than flow assurance, that has studied the intersection between flow assurance and process. So here I'm showing a study from an inlet to a manifold where we can see slugs. In this study in particular, we're looking at slugs in the developing region. So multiphase flow conditioning is trying to address some of those missing elements that perhaps we didn't look into in flow assurance, because flow assurance was looking at studies for long flow lines, and process is looking at separation. But that interface between both can be, in some cases, can also create some disruptions. And we can disable a separator by wrongly designing the upstream piping. So here's an example of what I'm talking about with multiphase flow conditioning. Here's a study where they did some CFD simulations of a separator with two inlet geometries. One had 2 pipe diameters of straight pipe ahead of the separator. One had 10 pipe diameters ahead of the separator. And this is the side view, and this is the top view. And you can see that the inlet that had only 2 pipe diameters after this elbow, you can see that the fluids enter this inlet vein distributor that is supposed to help you maximize the residence time and the efficiency of the inside the vessel. But you can see that the elbows effect are still carried into this inlet device, and it's not able to correct that momentum. And you can see that most of the flow is going in one direction, and the other part of the separator is actually being underutilized. However, if you extend the straight pipe length to 10 pipe diameters after the elbow, you can see that the inlet vein distributor is getting closer to an even distribution, which would aim at using more efficiently all the volume and area and all the components inside of the separator evenly. So this is just an example of how you can mess up quickly a separator by just installing these fittings in the wrong place. So again, as I mentioned before, multiphase flow conditioning resides between flow assurance, the long flow lines studies, and the process faults, and it's meant to address all these interface issues that may be created here and that not many people are aware or know that they should be looking for. So there are multiple studies that can be done. I'm not going to go into detail with this, but just to give you an idea, there are multiple studies that can help you identify if you have potential for multiphase flow conditioning issues. From the proper multiphase flow characterization, where you can understand what kind of slugs are coming into a separator, understand if you have droplets flowing into a separator, understanding the effect of fittings like chokes, valves, elbows on the fluids, helping to mitigate issues that weren't created in the flow lines, like severe slugging. Those slugs, if you can mitigate them before they reach the separator, you can reduce many issues. And another area can be multiphase flow splitting, where you can address the way multiphase flow splits into multiple processing trains, where the parallel processing trains require that the multiphase flow is split more or less evenly, so they have the highest efficiency. So all these studies kind of help you address different issues that help you alleviate flow-induced vibration, do a better job designing and your separator, troubleshooting, the way we handle flux, and like I mentioned, the efficiency in parallel processing trains. These are the situations where multiphase flow conditioning is more critical. Well, in subsea processing, you have very little access. Once you design and deploy a subsea processing unit, you have very little chance to address mistakes in the design. So you want to make sure in these situations you check that before you deploy. And also in small areas like top-size production facilities or FPSOs where the space is limited, you want to make sure that you check for those places where potentially you may have these issues. Compact separation. So when you have compact separation, these type of separators have very low residence time, and compared to the traditional separators, which may be more forgiving because you have a larger residence time, you want to address it and make sure that you give it a better chance to succeed operationally. And as I mentioned earlier, in multiple processing trains. Okay, I'm going to give you a couple of examples of flow characterization. So in this case, I'm talking about a case of liquid-liquid flow, or imagine an oil-water separator. And we're analyzing different fittings that you're going to have at the inlet of this separator. And you're deciding which one do I want or which one do I want to avoid. So I'm going to show three examples of three geometries. First is a blind T, where you can see that from the inlet to the outlet, if you have a blind T, you create some changes in the flows, velocity streams. And you can see on the right here on the turbulence dissipation from the inlet, the cross-section of the inlet compared to the cross-section of the outlet, you can see that we have created a significant change in the values and in the distribution of this higher energy dissipation. If we look at the different values of the turbulent energy dissipation inside the blind T, we can convert those values into droplet sizes. And then eventually we can come up with a distribution of droplets that will be coming out of this fitting. Similarly, we can repeat this exercise for different geometries, such as a long radius elbow, where we can see that the velocity streams are more or less parallel. And we can see that this fitting in particular is more gentle to the flow. And repeating the same methodology, we can come up with the turbulence, energy dissipation distribution along the way, and come up with a droplet size distribution. And again, for an impacting T, where we have the flow coming from left to right and going down, we can see that again, we're creating disruptions in the flow and making this additional residence time for the flow inside the fitting. And similarly, we can come up with a droplet size distribution. So here I'm comparing three different droplet size distributions for the three examples I just showed. We can see that the long radius elbows is shifted towards the larger droplet sizes compared against the blind T and the impacting T examples that are more towards smaller droplet sizes. So what is the importance of this? The problem with this is that if you're designing a separator or if you're analyzing the performance of a separator, all the different methodologies more or less are based on a similar principle, which is coming up with a separator droplet cut size. And the separator droplet cut size, just for the sake of this explanation, is just a diameter that is assumed that any droplets smaller than that diameter will not be separated, and droplets larger than that are only the ones that are being separated. So the problem is that, go here. All right. So based on the droplet cut size, the long radius elbow, if you integrate the curve, the area under the curve, you will have, this will become your fraction of droplets that are not being separated. But if you integrate that area for these other cases, like the blind T, you have a much larger area of droplets that you have not separated. And that can be an increase of around 250% in the oil droplets that you are not separating in this example. And that could be the difference between meeting the spec and getting in trouble with your local authority, with another company that is handling your fluids. So you can see how these decisions that some people may seem may not seem that important actually have consequences that may get you in trouble by not conducting a proper design. All right, let me move to the next slide. And all right, here's a second example. I'll try to move faster. Take too much of your time today. This is what's done in Star CCM. This is a CFD simulation of a butterfly valve. So here's a geometry of a butterfly valve with a plate in between that moves to adjust the flow rate. Here's the the geometry in star CCM. And since I realized that there were these 2 points where you have higher velocity and more interest as you're squeezing fluids through the valve, I created 2 spots where higher mesh density. So here's the result of the mesh with higher density in those particular interest areas. And similar to the other exercise that I showed earlier, I come up with turbulent dissipation rates that allow me to observe the points where there's higher turbulence in the valve. You can look at the velocities. So if this, you can see that the red arrows, vectors, are velocities that reach close to 150 meters per second because of the reduced area here. So you can imagine that high velocity, high turbulence, they're just spots that have a high potential to create smaller droplets that can create later on issues in your production facility. Anyway, now I want to bring everything together. So we talked about earlier about flow assurance and the multiple issues that require studies from the modeling point of view, labs, fluid samples. And on the other hand, we have the process folks who do studies on sizing vessels, qualifying new technologies, putting on instrumentation, analyzing performance. But sometimes there are issues left over that are either, they can be interface issues that require the integration of perhaps a basis of design of what is the output of the flow assurance studies that can become the input for the process faults, issues that are forgotten from both disciplines that can be addressed and verify the design. So I think multiphase flow conditioning can become useful to help close that gap. Some final issues on multiphase flow conditioning. I'm showing here a figure where I'm gonna just show here. There are issues of liquid carryover and slugging that are either created from flow assurance issues, or there are actually liquid carryover as a consequence of not understanding what's coming into your separator. If you have a flow with large amount of droplets in train, that's imagine an almost invisible mist of droplets that is very difficult to separate. And if you have not properly designed your separator with the right internals and the right residence time to address those small mist of droplets, those droplets are going to carry over and continue to bother you all the way onto your compressor. And then the compressors have limitation of how much liquid they can handle. So then you're gonna have to have shutdowns because the compressor cannot handle liquid. Also, liquid in the gas is not good either because you may end up in your flare, and then you may have an issue on the specs of the gas that you are going to flare, and now it has contents of liquids that you didn't want there. Similarly, when you have slugging, if we follow, instead of the gas stream, we follow the liquid stream, slugging can create mixing of the oil and water phases, and that mixing can create issues later on in your water separation tanks or separators that they are suddenly not meeting the specs. And it's not necessarily an issue with this particular piece of equipment, but it's an issue that started earlier in the process. Finally, we have other issues that are like related to integrity that are like such as flow-induced vibration. Those are the forces, as I mentioned earlier, due to the slugs that have a high momentum. These forces can be in different directions, and you basically need to address them properly so you know how much spacing between supports and what kind of supports you need, so to avoid the damage to your piping upstream facilities, and you want to characterize them to avoid damage to the separator or the internals that are going to, if they're going to be exposed to those forces. So here, we're close to the end. Here's some good news. The good news is that we can fix this. This is a good paper that I would recommend. If you haven't read it, I always recommend this paper because it gives you an overview of idea of issues that are in the oil industry that can be solved. And so I don't want to spoil it for you, but basically it talks about how, we have issues on what in projects, the type of expectations in the industry of the range of flow rates that projects think they're going to deliver and the actual flow rates that are delivered after the project is executed. And there are multiple issues why this is happening. One of the issues is communications, and there are multiple issues. But the good thing about in this particular paper is that they break down into different areas of expertise and parts of a project. And the areas that are closer to the well, to the sand phase, actually have a lower chance that you can recover from those mistakes. Because of course they have more difficult access, right? If the closer you are to, once you make a mistake in a well or in the reservoir, it's very difficult to correct. But the closer you are to the surface in facilities, you have a better chance to fix those mistakes. The good news is that flow assurance and multiphase flow conditioning are both in this area of facilities engineering, and they have a higher chance to be corrected after oil starts being produced. But also, why wait until oil starts production, and why not start fixing those issues before, during the design phase? So anyway, for my conclusions, I would say that each of the flow assurance areas of expertise, as I mentioned earlier, can be very specialized. They have deep understanding of fluids, organic and inorganic chemistry, modeling, scale up. So either become a subject matter expert or SME, or if you're in need, then look for their advice, because you would appreciate it later in the design of your project. We can disable a separator by wrongly designing its upstream piping, but we can also easily correct the multiphase flow conditioning issues by selecting simple piping components that help you alleviate those issues. And flow assurance and multiphase flow conditioning have a large impact in large projects. So don't underestimate them, and just be aware of them. Thank you very much for your time. And this is a list of the references that I mentioned during my presentation. And I want to thank Acknowledgements. Thanks, and thank you, University of North Dakota, for hosting me today. So thank you very much.
Thank you, Dr. Carlos, for the rich presentation. We will open it now for questions. I will start first. Based on your experience, do you think it's better to, as PhDs, for example, is it better to spend time on revising the modeling approaches used and try to improve them, or it's better to use what is available to provide properly, or to provide solutions?
Good question. There's I guess there's a balance between coming up with a new model that is going to produce a significant change in the way that people are addressing a problem, and just and what would the other way, or making minor improvements. I have seen both, and of course you want to see those leap changes in modeling, and they're both useful, but depends on the order of magnitude of the change that you can do. If you're refining a model that already exists and you're just adding a 0.1% improvement in the accuracy of that model, that may not be sufficient to have an impact. I mean, it may be in some situations be appreciated, but I guess my advice would be to be brave and, if possible, try completely different approaches to the ones that have been done before. You may fail at first, but it may pay off at the end. At least you prove that you can solve a problem in a different way. And because many people will try on the small improvements, and not many will be brave enough to make those leap change approaches in a methodology or a model. I don't know. Does that answer your question?
Oh yeah, you did. Thank you. Any other question? I can add another one in between.
Yeah.
And the industry now is more related into CO2 sequestration and stuff. With that comes the CO2 transport. On the surface. What are the main different challenges between transporting CO2 and other gases? If that's properly asked, I mean.
Yeah, no, I'm not very familiar with CO2 transport, to be honest with you. I'm familiar with CO2 present in other gases, and the problem with CO2, the one that comes to mind is it can be very corrosive. But besides of that, I really don't have much to add to that.
Okay, that's fair enough. Thanks. Any other question?
I have a question. Thank you for your presentation. That was very fruitful. My question is about the multi-phase flow modeling using computational fluid dynamics. I saw in your presentation that you had a couple of projects in that sense. So what do you see the challenges of the multi-phase flow modeling using CFD?
Yeah, so the challenges, I guess, are by the way, the examples that I showed, they were assuming dilute flow, right? So when you move from dilute flow to dense flow, the interactions, for instance, of droplets, when you're having dilute flow, you assume that the interaction of the droplets, you can neglect it, right? But as you move to dense flow, which is most or many situations in multiphase flow are in dense flow, they become computationally, they grow in complexity exponentially, right? So modeling dense flow and multiphase flow, considering a two-way coupling, as I show you some of the pictures that I show, let me see if we can use one. You have not only two phases, you have 3-4 phases in some cases. This picture I wanted to show. When you have solids, gas, oil, and water, that's reality. So having 2 or 3, 4 phases, it becomes more and more complex. And so depending on which problem you're trying to solve, well, we as engineers, what we do is we make assumptions and we simplify. So maybe you're trying to solve a solids transfer problem. And so when solving the solids transfer problem, you ignore the gas phase and you only do, or you ignore the oil and water and just assume you have a single liquid phase and keep the gas. So simplifying the problem and making the right assumptions before the problem becomes so complex that it's unmanageable or it takes too long computationally to solve and to get efficient results. When you're in a graduate school, you have plenty of time to run your simulations and you can wait weeks for results to come out. But when you join the industry, people want answers before the end of the week, right? Sometimes they need answers before the end of the day. So you have to be able to switch back and forth between your long-term studies and studies that give you an answer that's good enough for a solution right now that may not be 100% accurate, but has enough information just to make the right decision to solve an issue in the field. So, yeah.
Thank you so much.
Yeah.
Other questions? if we don't have questions, Dr. Carlos, if you have additional comments that you want to end up with, probably.
Well, if I want me to do some close argument, I guess I would say that, you know, multi-phase flow assurance areas are areas that are traditionally linked to the oil industry, but they're not limited to the oil industry. So I would motivate you to study them and become expert in these areas. But keep aware that there are other industries that might use this expertise. So developing expertise in fluids and fluid flow, heat transfer, that will always have applications in many industries. So I will encourage you to stay sharp and stay becoming an expert in areas that have a broad range of applicability, I guess, my message.
I got that point. Thank you for the valuable advice. I think if we don't have more questions, we would like to end up the session. Thank you again, Dr. Carlos, for the time and dedication to support the student community. And with this, we will end the presentation and to another one. Thank you all.
All right, thank you.
Thank you.